Predicting the formulas of ionic compounds. The guiding principle here is that a compound must be electrically neutral, having no negative or positive charge. For a compound to be neutral, it must have the correct ratio of ions. And remember, the cation supplies positive charge, the anion supplies negative charge. This ratio is achieved through the subscripts in the chemical formula. The subscripts will be related to the charges on the cation and anion. Say my cation is some metal ion with charge A+. My anion is some nonmetal with a charge of B-. This means that the positive charge supplied by the cation has to equal in magnitude the negative charge supplied by the anion. One simple way to achieve this is to take the magnitude of the charge on the cation and use it as the subscript on the anion. By the same token, we take the magnitude of the charge on the anion and use it as the subscript on the cation. This would lead to a chemical formula MbXA, and then you need to divide A and B by the greatest common denominator to get the empirical formula. In other words, to make sure that this is the smallest whole number ratio. Let's look at an example. Let's say our cation is tungsten 4+, symbolized by W4+. Let's say our anion is sulfide, S2-. We start out by switching the charges for subscripts. So, this gives us W2S4. This is the correct ratio, but it's not the smallest whole number ratio. Both 2 and 4 are divisible by 2. Dividing both by 2, we get WS2. That is the correct formula. And the name of this compound is tungsten 4 sulfide. Now let's bring in electron configuration and Lewis symbols. So we're going to consider the ionic compound formed between magnesium and chlorine. The electron configuration of magnesium is 1s2, 2s2, 2p6, 3s2. The 3s electrons are valence in magnesium, and everything previous is core. And 1s2, 2s2, 2p6 is the same as the noble gas configuration of the element neon. So, if magnesium loses 2 electrons, to become magnesium 2+, that's a stable ion because it has the same electron configuration as neon. Chlorine, on the other hand, does contain the neon core, but it's very close. It's 1 electron away from getting to argon. Right? Argon ends in 3p6. So rather than lose these 7 valence electrons, chlorine's going to gain 1 electron. So if we take chlorine and we add an electron to it, we get the chloride ion that has the electron configuration of neon, 3s2, 3p6, which is the same as the electron configuration as argon. Now, the electrons that magnesium loses aren't lost in a vacuum. They're going somewhere. And the electron that each chlorine atom gains comes from somewhere. In fact, the magnesium donates its electrons to chlorine. Each magnesium atom donates 1 electron to 2 chlorine atoms. Here we can see magnesium, neutral magnesium. It's got 12 protons in its nucleus at the center and 12 electrons in its electron cloud. Over here we have 2 chlorine atoms, 1, 2. Each one has 17 protons at the nucleus and 17 electrons in the cloud. Now a chlorine atom is smaller than a magnesium atom because of having more protons in the nucleus. Now 1 electron from magnesium goes to one of the chlorine atoms, turning it into a chloride ion. And another electron from magnesium goes to the other chlorine atom, making the other chloride ion. These still have 17 protons in the nucleus, but now they have 18 electrons. They're larger because of extra electron-electron repulsion. And our magnesium is left having 10 electrons, but still 12 protons. So what's the charge on magnesium? Well, charge equals protons minus electrons. 12 minus 10 is 2. So this is how our ions are formed. If we want to look at it in terms of Lewis symbols, here's a magnesium Lewis symbol with its 2 valence electron. Here are the chlorines. Each one has 7 valence electrons. So each chlorine really wants 1 electron. The magnesium gives 1 electron to the first chlorine, gives the other valence electron to the second chlorine. And now the Lewis symbols for the ions have brackets. Inside the bracket goes the element symbol with dots corresponding to valence electrons. Notice for the Mg2+ ion there are no dots because to make the cation it has given up all of its valence electrons. Each chloride ion now has 8 valence electrons and has a charge of -1. The charges go in the upper right hand corner outside the brackets, and of course there are 2 chloride ions. So on the right we have the Lewis symbol representation of an ionic compound. Can you do a similar analysis for calcium nitride? By the way, what's the formula? Use the switcheroo method. Do you need a hint before you pause your video? Well, calcium's in group 2, so it'll form a 2+ ion. Nitrogen's in group 15. What's the charge in group 15? It's 3-. Pause your video now and determine the formula of calcium nitride. Then unpause it and see if you got what I got. Being in group 2, calcium is a 2+ ion. Nitride, being in group 15, is a 3- ion. When we switch subscripts for charges, we get Ca3N2. 1 is the greatest common denominator, so answer choice D is correct. To do the Lewis symbols, this means we're going to need 3 calcium atoms and 2 nitrogen atoms. Here are our Lewis symbols for the atoms. Here are the electrons being transferred. So 1½ calcium atoms are needed to supply all of the electrons that one nitrogen atom needs. Now all of the electrons have been transferred. In the end, here's the Lewis symbol for a calcium ion. 0 valence electrons inside the brackets, because it lost both of them, and a 2+ charge. And there's 3 calcium ions. Each nitride ion has 8 valence electrons, because it started with 5 and gained 3, so 8 dots inside the brackets, and then a charge of 3-, and there are 2 nitride ions.